of which has been going on here, and trying to understand some of the major puzzles in the high-temperature superconductors. So one of the themes I want to talk about is this so-called strange metal phase in the cuprates. So let me just introduce that. So the cuprates are discovered in 1986, and they go superconducting at rather high temperatures. And another wonderful thing about them is you can make big wires. So this is a wire of YBCO. And this is a company here in Bangalore, which is using these wires to confine plasmas and eventually maybe lead to fusion energy. Then their name for this wire is a bit unfortunate. So there's an M is cut off. That's MAGA. For magnetic gain, that's what it stands for. Okay. I don't know when they chose that name, but okay. Oh, sorry, can't see the M. Yeah, this company is right near JNCA, so maybe some of you know about it. It's very exciting. Okay, so this is a physicist phase diagram where you change the concentration of oxygen, and that changes the doping concentration of holes, as I'll say in a little more detail later, in this copper square lattice of copper ions. And at some doping, you get the very high critical temperatures. So most of this talk will be really about above the TC, where you have actually some very interesting crossovers, at least, behavior in the normal state, as we call it. And the reason we want to study the normal state is that if we want to have any hope of understanding the value of TC and why these materials, 40 years after their discovery, are still the champions of the best superconductors with such high TCs by far at atmospheric pressure. The only way we can understand TC is if we also understand what's above TC. Okay, so but if I look out here on the right-hand side, where the TCs are low, everything seems to be very familiar, and it looks like any ordinary metal like copper or gold in its properties. So this is what we call the Fermi liquid theory, and in particular, the theory used to describe phenomena is the quantum Boltzmann equation, and this works in a dense gas of electrons because the exclusion principle makes collisions rare. And the main assumption in this theory is that successive collisions are statistically independent, so it ignores any multi-particle entanglement that may develop because of the interactions. So the theory has been extremely successful, and one of its predictions is that the time between collisions, or some sort of relaxation time, diverges as temperature goes to zero as the second power of temperature, and also inversely as the strength of the interaction. And one of the consequences is that the resistivity goes as T squared at low temperatures. Okay. So you can ask, well, let me just crank up the interactions. Maybe this theory is going to break down. And so that was the kind of question I asked in this book. And argued that there's kind of a limiting time, which is now called the Planckian time, because it's the only thing that appears here as Planck's constant, and temperature. Kb is just an artificial unit because you measure temperatures in units of degrees Kelvin. Okay, so this time does not involve the strength of the interaction and seems like a fundamental limit for the validity of the Boltzmann equation of rare scattering between particles. Okay, but as we'll see that there are such states, both experimentally and theoretically, where the time is exactly of this Planckian time, and which therefore cannot be described in the quasi-particle picture of Boltzmann and Landau. Another interesting to observe is that you can crank up the interaction to make the scattering time short, but eventually at low enough temperatures, because this diverges as T squared, the time tau will be bigger than this time. And so it seems as if this theory should always work at low enough temperatures. And that's what most people thought until most prominently in the cuprates, we started to see that this simply is not true. And it's not true in this strange metal regime, where you see resistivity, which is linear in T down to very low temperatures. And there's no clear explanation for this in the Boltzmann theory, even after you include phonons and other scattering events. So it became slowly clear that we need some fundamental revision of how we think about this transport. Now, the linear NT is, of course, the most famous experimental observable, but there's more informative, more information appears from looking at the frequency dependent of the conductivity. So these are measurements of reflectivity of one of the high-TC superconductors, both the real and imaginary part of the conductivity. And through some very general arguments, you can express this in terms of some frequency-dependent effective mass. The frequency is omega is the frequency of the light, and the scattering time tau. And through a careful analysis of these experiments, in particular this paper, showed that this tau is precisely Planckian, that at low frequencies about a 1 over temperature, and it obeys the scaling form. It scales as a function only of omega over t. So that's one of the most remarkable things about this Planckian time is that it does not depend on the strength of the interactions, which is completely in contradiction to the whole Boltzmann approach. You see this kind of Planckian time in many materials with very different energy scales, including now in twisted bilayer graphene. But the scale is still the same. So the fact that you can relax in a time that's, in a sense, fast as possible, independent of the strength of the interactions. Okay, so that's the puzzle that's been around for a long time, and I'll give you my thoughts on how we understand this Planckian dynamics by talking about some simpler systems first. Okay, so the strange metal I should also mention is ubiquitous in other materials. I've already mentioned graphene, and I'll show you a few other materials. Basically, every correlated electron superconductor has a strange metal associated with it. But even though it's ubiquitous and universal, there must be something different about the cuprates because they are the champions in high TC. So that's also, it has to be, you need some theory which is kind of universal, but also make some allowances for the fact that something is different in the cuprates. And that's what I'm going to propose. Okay, so this, continue. All right. So I'll begin not with strange metals, but with strange semimetals. So these were actually predicted theoretically by us in just plain old graphene. So if you just take ordinary graphene, which is undoped, now you all know it has a relativistic spectrum. Here's the chemical potential, these are the occupied states, and the dispersion of the electrons and holes is exactly that of a massless Dirac particle, except the velocity of light is replaced by the Fermi velocity. So it turns out, a lot of the early work on graphene was, well, these are, treat them as free particles and see what you get. And it turns out they, in fact, here, a combination of various things give you very strong interactions and sort of a breakdown of quasiparticle picture. In fact, it shows you Planckian dynamics, but in a relatively simple setting that you can actually compute things reasonably reliably. So the basic reason is, first of all, the relativistic dispersion spectrum that leads to some critical state. And the other is that the Coulomb interactions are not screened. And in fact, they're characterized by a dimensionless coupling constant, alpha, which is the analog of, sorry, now things are getting cut off. I don't know what to do. Okay, maybe I'll use the board. So that's alpha is E squared over H bar epsilon VF. So that's the analog of the fine structure constant, except the velocity of light has been replaced by the Fermi velocity, and epsilon is the dielectric constant. Yeah, okay, I wonder if this can do. maybe I'll just show you this, if you don't mind. This may be another way to do it. So, yeah, that's not bad. Okay, now I make it bigger. Then you can see the whole screen. Yeah, well, you can see everything, right? Yeah. Okay, let me do it this way then. I don't have any. Okay, perfect. There, okay, great. So here, this is what I was saying. There's alpha over there. And now it turns out this is a dimensionless coupling constant, and it has a flow under Rg that you can work out. It decreases, but very, very slowly. And so at long enough distances, the Coulomb interaction becomes irrelevant. They go to zero. But there's a very slow flow, and over the temperature scales that we are working at, we can just imagine alpha as a constant. So if alpha is a constant, then in fact this whole theory is a structure very similar to conformal field theory, and it is strongly interacting conformal field theory, and from that you can say a lot of things. For example, you can say that the conductivity is in fact about E squared over H, some function of frequency over temperature. So normally here there's some kind of Drude expression. This is telling you that the scattering rate is Planckian, just kBT over H bar. And also the overall conductivity, and this is different from the cuprates, is of order E squared over H. Okay, so this is what we predicted in these early papers. And there's this beautiful work by, so this is I'm going to have to do by my hand now, it seems. Yes, okay, so there's this beautiful work by Feng Wang, group of microwave conductivity, where they see exactly what we predicted. Even the scales are reasonable, where your frequency, conductivity depends only on this ratio of frequency over temperature. Another exciting development and a consequence of this quantum critical behavior is that this fluid in graphene doesn't flow like ordinary current in a metal. It's in fact, since the graphene is very clean, it's more like water flowing in pipes. There's a viscosity associated with it, and that leads to some remarkable effects. So it's more like a hydrodynamic flow. And there's, so among the consequences of this hydrodynamic flow is that the Wiedemann-Franz law is badly violated, as experiments done here. And there are many other things that they measured, which I'm not showing here. And also, this beautiful experiment, which sees whirlpools in graphene. So again, I won't explain it in detail, but there's very good evidence here that as you flow current, you see a vortex here in the opposite direction, which is what you expect for water, but doesn't happen in an ordinary metal at all. Okay. All right, so I would say that this particular strain semi-metal is reasonably well understood. We can do some microscopic theory, and at least on the scale of the other strained metal and so many other materials, it has a common feature that the relaxation time is Planckian, but the overall scale of the conductivity is much larger in the cuprates than over here. Here it's E squared over H, which is not such a good conductivity. All right. So let's go on to strange metals then. And the approach I'm going to take to understand strange metals, as many others have taken, is to think about in terms of quantum phase transitions. So I won't go to the cuprates right away, because the cuprates are definitely the most complicated, also the most interesting. But here's another material. This is one of the pnictides. It's an iron-based superconductor. Again, the ions form a square lattice. And this is its more complicated phase diagram. So forgive me for all these lines, which are just in the paper. Let's just focus on the phases. So first of all, you have this red region, which they call non-Fermi liquid, and it has exactly the same behavior as in the cuprates. The resistivity is linear in T. So N here is 1. Okay. Then, however, what's different from the cuprates is this STW region coming down. What is STW? It stands for spin density wave. And if you look at the spins on the iron, actually, this is not quite right. So they form a regular structure where half of them are up and half of them are down. And that's the spin density wave. And what you notice is that the spin density wave vanishes at some point inside the superconductor, and there you have what you call a quantum critical point, QCP. So then, as a function of x, if I just look at the magnetism, there's a phase transition in the magnetism. It forms this pattern all the way up to the QCP, and then there's no magnetism on any given site. So the scenario is that, you know, this QCP is the central actor here. It's this QCP that's controlling the strange metal. So if we understood the critical fluctuations of this QCP, the way we can understand them very well in graphene, that will tell us why you have a strange metal here. And similarly, if we understood how the critical fluctuations pair the electrons, that will tell us why Tc is high. And in fact, it is a maximum right near the QCP. So this QCP seems like just the right thing to study the rest of the phase diagram. It's a thing you should try to understand. Okay, so that seems very reasonable for these pnictides. And a lot of progress has been made, and although there's a bunch of subtleties trying to understand this red region from the QCP, even for this case, that I hope to get to fairly soon. Okay, so that's one story we can say, that really what we should try to understand is strip everything down to its basics, that you have some parameter S. As you tune the parameter S, there's this magnetic order phi. It's non-zero in this spin density wave. It's zero here. And just work out a theory of this transition, and everything will be understood. Okay. And that's, as we'll see, that it's not as simple as that, but that's a good starting point. Okay, so that looks like the way we should think about at least these pnictides. So now let's try to carry that over to the cuprates. And you see a very different phase diagram. Now this spin density wave, which is now called by these authors the antiferromagnetic insulator, it's nowhere near, it vanishes well before the highest Tc. Vanishes already over here. And in fact, there is no QCP between the antiferromagnet and the Fermi liquid, which is over here, or the ordinary metal. There just doesn't exist any connection. So it doesn't seem reasonable at all to think of this vanishing of the antiferromagnetism as the underlying QCP that's controlling the whole phase diagram. I think most people, I think most people agree with that point. But that just simply cannot work just by simple look at the phase diagram, whereas completely is the case in the pnictide. It's also very convincingly the case in the electron-doped cuprates. But those have a lower Tc. But in the materials with the highest Tc, it's clear something different is going on. This QCP is nowhere near the highest Tc or the strange metal. Okay, so what is going on? Well, the proposal that we made is that there is a QCP at this P equals Pc, but it's hidden. And it's a QCP not between the antiferromagnet and the Fermi liquid. It's between this pink region here, which is called the pseudogap metal. And towards the end of my talk, I'll show you a whole bunch of experiments on this metal. But right now, let me just proceed by saying that this is a metallic state where, again, the Fermi liquid theory doesn't work. But it's not like the strange metal where there's this Planckian relaxation. Here, the relaxation is actually much slower, and it's more like a Fermi liquid, but many of the details are not like a Fermi liquid. So we, in fact, have proposed a theory for the pseudogap metal, which I call FL star. Here's a cartoon wave function of it. It's associated with the spin liquid and with some entanglement, and I'll come back to that towards the end. Okay, but the point of view now is that there is this new phase of matter, which we call FL star, which will have a QCP between FL star and FL. So there would have been a QCP, but because of the onset of superconductivity, the QCP disappears. Okay, so that's something is possible. In fact, a theory shows that that is exactly what happens. And that's because there is no broken symmetry. There's no order parameter in this FL star as there was in the AF. So the onset of superconductivity actually completely destroys this FL star phase. Nevertheless, this PC we propose is the right way to start understanding everything that's going on. Okay, and hopefully if I time things right, I'm going to show you at the very end some recent experiments which I claim support this point of view. Okay, so but for now, just accept that this is correct. And there is, in fact, underlying the cuprate. So this is our proposal to how to think about the cuprates. We're also going to think about it in terms of a quantum phase transition. But a quantum phase transition between this exotic phase we call FL star, and the ordinary metal. And these two phases are also distinguished by the condensation of some field phi. But this is not a broken symmetry. This phi is a Higgs field. It carries gate charges and is associated with entanglement here that's different from an ordinary metal. Okay. Anyway, so then we have the same old phase diagram, except the interpretation of phi is different that we had for the nictides. So we can put it all together and say that this is a generic phase diagram for the strange metal. And all you have to do is just work, for any quantum material, there's some common theory. And the difference with the cuprates is simply that phi is a more exotic object. It's not a broken symmetry. Okay. So there is some difference, but other than that, there's a universal type framework for thinking about this strange metal, which presumably is associated with this so-called quantum critical fan. Okay, so those ideas were around for a while, but slowly through our work with graphene, we realized there was a problem with this idea. And the problem is that, in fact, this quantum critical fan, as I've described, is in fact not a strange metal. So here the theory is you have a metal and another metal. There's some kind of phase transition at 0 temperature, and near the critical point, all the fluctuations give you a strange metal. Well, turns out the answer is no. And the reason it's no has to do with this phenomenon called drag. When you look at the low energy theory of any critical point, there's a conserved momentum. And in fact, it was that conserved momentum that was responsible for the strong violations in the Wiedemann-Franz law that were measured here. So there's a similar thing here, not quite exactly the same. But the conservation of momentum in the low energy theory implies that actually, even though you may break down quasiparticles in this regime, the strange metal transport simply does not appear. Okay, so that's something we slowly realized starting in 2007, and in fact, several calculations of transport in this regime by famous people were incorrect, because they overlooked this drag effect. I mean, roughly the idea is that there's some phi field which is fluctuating strongly and it's scattering the electrons, and that will lead to huge resistivity. But that's wrong, because the phi field is nothing but the electrons themselves. It's not as if you're losing momentum by that scattering process. And since the scattering is so strong, you can't think of phi and the electrons as independent of each other. They're just one fluid that's flowing together, sort of like the hydrodynamic flow in graphene, and that must mean that the resistance is actually 0.
So is this phi connected to the hydrodynamic behavior in any parameter of hydrodynamicity?
Well, it leads to this conserved momentum in this theory, yeah. So, right. So, however, in the real world, so this theory doesn't work at all. Unlike in graphene, the hydrodynamic theory works. Here, the hydrodynamic theory fails. Doesn't give you linear T resistivity, period. In graphene, you get a resistivity over E squared H because of particle hole symmetry. Here, there's no particle hole symmetry, so in fact gives you zero resistance. Yeah.
So this statement, is it true even let's say if you have some heavy band like in heavy
Yeah,
band?
no, so that's the caveat here. If you had a nearly flat band with lots of Ohm as in various models, then there would be, you have to go to really low temperatures for this effect to come in. But in the cuprates, there's no sign of any flat band at all. There's only one band with a big dispersion in photo emission. Okay, so what's the fix? Well, the fix is you have to put in impurities. So impurities are absolutely crucial. Actually, they are in graphene too, but in a different way, as Arindam knows. But here, impurities can do several things. So there is a well-developed theory of effect of impurities on ordinary metals in the presence of interactions, and is very successful. And those effects are present here too. But there's another effect. What impurities can do is that they can cause the system to fluctuate on the two sides of the critical point. So one region of the sample here could be on the left of the critical point, the other region could be on the right. So that's what's called Harris disorder, and in fact, by far the strongest effect. And that's what you really have to work through, include this Harris disorder, and then see what happens. So this is what several of us have done, in particular Avishkar Patel did some very important work on this. And so from this, in fact, we do get what a theory that actually describes most aspects of the strange metal.
But it's the same thing with graphene. Having essentially the electron hole puddles is the same result.
Yeah. But I mean, the details are quite different, but yes. So like I said, we were very much inspired and learned a lot from graphene that eventually enabled us to see this, which many other people, I mean, the list of papers that are incorrect is longer than the list of papers that are correct, in my opinion. I mean, I think the reason this is subtle is that, people had assumed that drag effects are extremely weak in metals. Now that's true, and the reason it's true because electron-electron scattering is weak, or electron-phonon scattering is weak, and so you can really think of the electron and the phonon as independent degrees. But when you get to a system where the quasiparticle is breaking down, you cannot take the weak coupling point of view. So even in a relatively disordered material, drag actually is quite important. In fact, it's the strongest thing. All right, so this is kind of the insight that we got from all the holographic and graphene-like insight. So all that work was enabled us to see things here. Okay, so let me just describe the final theory. How am I doing on time? Okay, I'm doing okay. So what is this universal theory of strange metals? So what we see here, let's just strip it down. What would be nice to have is some solvable model. So we strip it down to the basics. You have a metal, and you have phi, and you have some disorder. So can you write down a model which has all those three ingredients? Don't try to make it too realistic, but at least try to make it solvable and keep those ingredients. So there is the SYK model, but actually the correct model to understand the strange metal is the so-called Yukawa SYK model, which appeared in various guises by various people, although this particular form and this paper by Estelis and Schmalian. So what is it? It's really very simple. You have a bunch of orbitals labeled by I, in which you put in these fermions, psi. And they all have, it's a flat band to begin with. So you have a flat band of fermions, and then you have a bunch of oscillators. It could be Einstein phonons or something, and they all have the same frequency. Okay, L labels the oscillators, and I labels these, just these, all states of the same energy of the fermions. Then you couple the oscillators to the fermions by this kind of electron-phonon scattering-like term, and And so you have the coupling GIJL for the phonon L to scatter an electron from site J to site I. So there's this coupling GIJL. And so this is an interacting problem you can't solve. But if you just make these numbers, GIJL, independent random numbers, that's all, this is solvable in the usual tricks similar to the SYK model. So you can solve it. In fact, the easiest way to do is just do diagrammatics and average graph by graph. And you find in the large N limit, these very simple graphs are the only things that survive. Where G is the electron Green's function and D is the phi Green's function. And the self-energies are just given by these very simple diagrams. And the more important point is that these G's are fully renormalized G's. You just have to solve these equations as carefully as you can.
The size of fermion couplings.
What? Psi of fermions, correct. Yeah.
It's not my one.
You can make them iron or two, it won't change very much. Okay, everyone clear what the model is? It's really as simple as it gets. And these kind of equations have been written down in all kinds of contexts overall, but nobody ever solved them completely, self-consistently for this simple case in 0 dimensions. And the other insight that comes from the SYK model is that making these random makes this exact. This is the exact solution in the large N. All right, so what you find is that in fact, generically, no matter what the value of this omega 0, this is always a non-Fermi liquid with some strange power law singularities that you can determine exactly. But more importantly, it's Planckian. If you look at the finite temperature behavior or the non-equilibrium behavior, you find that it relaxes just time over h bar over kt, and this time is independent of the strength of the electron phonon coupling. Low enough temperatures is always Planckian. And this is like the fastest possible relaxation rate. And somehow what's happening is that the quantum entanglement makes this YSYK model a champion in reaching thermal equilibrium as fast as possible.
There is any RG study on this available.
No, RG doesn't really help here. You have to do the thing full self-consistently. There are Monte Carlo studies that fully confirm this. The limit is very smooth. I don't know how you do RG on this. The thing about RG is that you assume that you can integrate out high energy scales to determine the low energy behavior. But here you really have to do things more self-consistently because the damping of the lowest energy scale is actually determined by excitations with the energy over a kT at higher energy. So it has to be much more self-consistent than RG. So RG doesn't quite work for these problems.
So this relaxation time is for what quantity specifically?
You can define anything. You can do a quench or you can do keep it up or something. So of course the constant term would depend on exactly how you define it. The most convenient thing that people talk about is out of time Botox. And in this case, this model also has the maximal chaos 2 pi h bar kt over h bar.
So this model also has residual entropy.
Yes.
Same, the value can be calculated here.
You can calculate it, but it's different from the SYK model. All right, now, so that's very exciting that it has Planckian relaxation, but Similarly pointed out something else. It has a 0 temperature entropy, which cuprates definitely don't have. So some things work, but not most other things. And it's in 0 dimensions. So what do we do? Well, basically what works is you just take this model and make it realistic. You take all the 3 terms and you make them realistic. So first of all, the fermions, which are completely in a flat band, you give them a dispersion. So you get a Fermi surface here, and we have some dispersion E of k. And similarly for the bosons, you give them some dispersion. And then finally, you put in the Yukawa coupling, and you make it local. So it only depends upon the local position. and you also put in some random. So the things in blue are random functions of space with zero mean and some correlation. This V of R is the basis of disordered electrons, but actually the most important effect comes from this G prime of R. And the reason being is this G prime, which actually determines the local position of the system relative to the QCP, the particle behavior that Arindam mentioned. So this is what you have to include. Anyway, so this model as written down, of course, it's impossible to solve, although IISc now has beautiful quantum Monte Carlo studies of essentially this model, which verify what I'm going to say now. So what we did first was, okay, we felt confident from the success of the large N model for the Yukawa SYK. We said, let's just solve it in exactly the same approximation. We just take this model and write down the same old equations. These are the two equations I showed you. Except now, of course, things depend on position and momentum, and there's various stuff from the impurities that you average. But anyway, this in the end is just these equations that you can write down that we have now solved numerically on a computer, at least at G equals 0. Sumillan has also done similar things. And you can also do a similar thing for the conductivity, which I'm not sure. Anyway, so you can solve them, and what you see is here are the basic things you find. First of all, if you look at the electron Green's function, it's what's called a marginal Fermi liquid, meaning that it has some inelastic scattering rate, which is a linear function of frequency or temperature. And this scattering rate for the electron Green's function comes both from the Harris disorder G prime and also from the impurity disorder. Whereas the effective mass gives you this log fraction. And then when you compute the conductivity, you get one very important fact, that the transport scattering rate, which if you compare this transport here with that, this is the quasiparticle scattering rate or the inelastic scattering rate for the single particle sector. So this had a term which is associated with V, associated with G. But there's now a term here associated with G. This V squared is the analog of this V squared. That's the elastic scattering rate. The G term disappears. And this is exactly what I was saying earlier. In the absence of disorder, the resistivity is 0. The uniform electron phonon or electron boson coupling does not contribute to the transport. Only the random part does. And then you also have a corresponding log behavior in the effective mass. And in fact, this form of the conductivity is precisely the form that was used by that paper by Landau Merrill I showed in the beginning of my talk to fit their optical reflectivity experiments. The form that they came up with around the same time as our paper, just by thinking about the data, is exactly what comes out of our theory. And now we can also do full solutions, and you can get, this is the resistivity at different doping. So near the critical point, it's linear, and then as you go to the Fermi liquid side, you get T squared behavior. There's actually even a TC in this material, in this model, but I'm not going to take that too seriously.
So this T log T specific T is also seen in Q.
Yes, yeah, thank you for pointing out. So one difference from the Yukawa SYK model in 0 dimension is that the entropy is T log T, it's not non-zero. So it does vanish as T log T. Okay, all right, so that's basically it for the main part of my talk. I've told you about the theory of Planckian dynamics in graphene or semimetals, and then this is our theory for metals. There's many other things to think about, short noise and Hall effect, and we've written papers on that, and we're pretty optimistic that those will also work out. But those are harder things. Maybe even you can try to work out the effect of high intensity light, nonlinear response, We have some papers on that too. It seems to be at least roughly consistent. So we're pretty happy so far. There's no obvious experiment that says you're wrong. Okay. All right, but underlying this whole approach was the assumption that, at least for the cuprates, that there is a QCP associated with this FL star phase without any broken symmetry. There is an underlying QCP for the cuprates, and so now we have to come back and see. Let me tell you in the remaining 10 minutes a little bit about that pseudo-gap regime. Okay, so I said in the cuprates that the strange metal connected to a hidden QCP between this pseudo-gap metal here and this Fermi liquid, and it's the onset of superconductivity that kind of hides it. Because once the superconductivity appears, as you go from here to there, you don't see any phase transition. Okay, so is that the case? So one of the earliest indications that something is going on in the superconductor was looking at the vortex core. So we all know from BCS theory that the core of a vortex is where you get the normal metal. Okay, so one way to look at the metal underlying your superconductor is look at the vortex core. And here I'm telling you that the metal underlying the superconductor is totally different. I mean, experiments show that. But if you go to low temperatures, look at the vortex core. If you look over here, then you see this famous checkerboard structure, which appears at finite energy and a suppression of tunneling current at low energy inside the core of the vortex. On the other hand, if you go to high doping,
this entire panel is inside the vortex core?
no, this is one vortex, that's another vortex, that's another vortex. This is the famous hot
checkerboard inside the vortex.
No, so this region here is one vortex. This is work of Jenny Hoffman and Seamus Davis from over 20 years ago. Okay. And at large P, however, everything is okay. So the BCS theory predicts actually a large zero bias peak, not a suppression, but a peak. In the bulk of the sample, you have a D-wave superconductor, so there's a gap. When you get the vortex core, because it's gapless along certain directions, you get this peak. I mean, in an S-wave superconductor, you get these Degen-Matricon states, and in P plus IP superconductor, you get Majorana fermions. Here, if you do the analog theory for BCS, Landau Ginsburg, or Boguslavov-Degen, you get a peak. And you do see the peak, however, over here, but you don't see it here. So that's, I think, very strong evidence already that there are two different metals underlying the low doping and high doping regime, and so that perhaps in the metallic state at least, there's a quantum critical point.
These vortex without any magnetic field.
There is a magnetic field here. So that's how you get a vortex line.
No, so that is the reason, but it has not been mentioned in the phase diagram explicitly.
Yeah, sorry about that. Yeah, thank you for pointing that out. Okay, what else? Well, so here I go to the underlying microscopic of the cuprates. It's a square lattice of spins which form an antiferromagnet. That's the antiferromagnet here, and then you remove fraction P of them. So you can ask, how many holes do you have? If I just look relative to the antiferromagnet, the density of holes is P. That's what this axis is. But relative to the fill band, since the fill band can have 2 electrons per side, the density of holes is 1 plus P. So Fermi liquid theory would say that this configuration, if it's a Fermi liquid, should have a Hall coefficient of 1 plus P. And in fact, that is exactly what you see. On the other hand, if you look at the Hall coefficient here in the pseudo-gap metal, you get something very different, P. And exactly how that goes from here to there is a subject of debate, but it's not, it's well established that you have a very different Hall coefficient here than you do here. Now this Hall coefficient P would make sense if there was antiferromagnetic order, but you see it well beyond the region of antiferromagnetic order. And so that's kind of a mystery. also telling you that there are two different underlying states. Then you can look at photo emission. In photo emission, you see this large Fermi surface at large P, and you see these mysterious Fermi arcs, which various people, including us, have argued are really pockets, and in fact, I agree with that. And if you ask for what is the size of this pocket, since there are 4 pockets, this is 1/4 of the Boltzmann zone, and there's a factor of 2 for spin. That means that the size of the pocket, each pocket has 1/8 the density, and so in units where this Boltzmann zone has area 1/4, and the full Boltzmann zone has area 1, the area of this pocket is P over 8. Okay. But it's mostly an arc. Now, if you look at STM, then again you see at low doping you see the arcs, and at high doping you see the full Fermi surface. So at high doping, if you look at this area, it's in fact in units where the area of this whole thing is 1/4. This area is 1 plus P over 8, and that actually works out. And at low doping, just boldly, the authors of this paper said, well, we only need to count the crescent, but didn't give any explanation why. And the area of this should then be P over 8, and that also works out. Okay, so finally, it said, Then there was this magnetotransport experiment. So what this is doing is measuring angle-dependent magnetoresistance. You apply a magnetic field at a strange angle and measure the current in this direction. And what they see is that the low doping behavior as a function of angle is entirely different from the high doping behavior. This is high doping, that's low doping. And these kind of pocket models do a much better job of explaining the angular dependence than anything else at low doping. And in fact, what this experiment shows very clearly for the first time, that whatever is this low doping pseudogap metal is, whatever the carriers are, they have coherent interlayer transport. So there's no way you get these complicated angular dependencies unless you can go in. You have some dispersion, coherent dispersion in the c-axis direction. Okay, I know I'm getting a bit technical, so now let me tell you about this FL star. What is this state? So I'm going to write, so this was proposed in 2003 with Sintil, who we all know, and my then postdoc, Matthias Voita. So there's a very deep theorem in solid-state physics called the Lettinger theorem, which says that the area enclosed by the Fermi surface is just the total density mod 2. And we argued that there can be other states, which are entangled states, where the density is shifted by exactly 1, rho minus 1. Rho is the total density, but in this case would be 1 plus P. And this state would have a Hall coefficient, which is P, rho minus 1. And the total area enclosed by the Fermi surface should be rho minus 1 over 2. So each pocket should have area P over 8, as I mentioned earlier. So these were states we found in certain models that involving spin liquids, and we've been working intensively on this since then. And there's very different ways of now understanding and even writing down wave function for this state. Let me show you, and since I'm running out of time, just a crude picture of what's going on in this pseudogap metal. So the picture is the following. We start from here a very simple picture of a spin liquid. So let's assume the half-filled system, instead of being an antiferromagnet, is a resonating valence bond state. Now we remove p electrons from this. So if you remove the electrons, so these are the sites we remove the electrons from, then each of those sites will have an unpaired spin. So this vacancy is sometimes called a hold-on, this is called a spin-on. And this carries charge but no spin, this carries spin but no charge. And these objects can now move around. And maybe the underdoped state, as many people postulated even early on, is just a gas of these hold-ons and spin-ons. There's just one problem with that. The recent experiment, this experiment of Ramshaw, So it's coherent tunneling between layers. But these holons cannot tunnel coherently between layers because they are fractionalized particles. And they require the C of singlet bonds to even exist. So there is no coherent tunneling of holons between layers, and so they cannot explain the ADMR experiment. So what's this FL star state? Well, it's a cousin of the state. So what we're going to argue is that the holons and spin-ons, as they hop back and forth like this, that gains you energy T. And to create these spin-ons required an energy J, but T is bigger than J. So in fact, these holons and spin-ons will bind to each other, forming a magnetic polaron, this green object. So the green object is just a spin-on and holon exchanging positions. So that's it. Draw a green dimer. And now this green object has the same quantum numbers as the electron. It has spin a half and charge E. So so you've gone through all this trouble of fractionalization and reconstruction. But why are we doing all of that? Well, because the point is the density of the green objects is P. It's not 1 plus P. The density of holes in the Fermi liquid theory is 1 plus P, but the density of the green objects is P. And this is only possible because you have this spin liquid with an emergent gauge field. Without it, you cannot do this. Okay, so now the theory FL star is just a gas of these magnetic polarons, as some other people call them. And you can do calculations on this model and get precisely this type of pockets of P over 8.
So why do you call it the magnetic polaron? Is it because
Other people call it. It's like in terms of an antiferromagnet, it's a hole with a cloud of spins around it. I don't like it actually, that terminology. It's a holon spin-on bound state. This is simply to connect with other people's work. Okay, so finally I'll conclude by mentioning this amazing experiment that came out last year, which I was very excited by. So this was, again, it's ADMR that I told you about earlier, but it is other high TC material, which has a very simple C-axis structure. It has basically AA stacking. And so because of the AA stacking, the Fermi surface structure along this direction is just a cosine. So for this cosine dispersion, there's something called the Yamaji angle. And what is the Yamaji angle? Well, so if you put the field at some strange angle like that, the electron orbit will be orthogonal to it. And various properties of the electron orbit will determine the period or the area enclosed by this orbit. Okay. Now it turns out at certain angles, in fact at the Yamaji angle, the area enclosed by this orbit is independent of where you are in the z direction. It's the same. Shape with the area remains the same. So effectively, you get a flat band in this direction, which suggests that there's a peak. The resistance should become high at certain angles. And knowing the Yamaji angle, you can then read off the area of this circle, which they said was this. Anyway, so they did that. So here's the Yamaji angle. That's the Yamaji peak. And from this paper, they said estimated to occupy the area of this pocket is 1.3% of the Brillouin zone. Their doping is 0.1, and P over 8 is 1.25%. So very close to what we predicted many years back. And this is a fairly non-trivial thing. If you take an ordered antiferromagnet, and then the area of these pockets is P over 4, whereas it's only when you have a spin liquid with these electron-like pockets in the area becomes P over 8. So this shows you something, another fact. There's a common misconception in the literature that somehow thermal fluctuations are the same as quantum fluctuations. They're not. Quantum fluctuations are totally different, and they completely change the shape of the Fermi surface, whereas thermal fluctuations don't. So in the electron doped cuprates, you will see area P over 4, but in the whole doped plane, you see P over 8, at least in this experiment. All right, so I'm done. So to quickly recap the main part of my talk, there's the SYK and the Yukawa SYK model. They give you solvable models of Planckian dynamics. And the two-dimensional generalization of this Yukawa SYK gives you a universal theory of strange metal arising from quantum phase transition in metals, basically any quantum phase transition. But in the cuprate, that quantum phase transition is sort of special because it doesn't have any broken symmetry. This is this FL star to FL transition, which I haven't really told you more about how we set it up. But to answer the first question I posed in my talk, could the existence of this spin liquid and the unusual order nature of this transition be the reason for the high temperature superconductivity? Okay, I think yes, but I certainly don't have any fully convincing argument. It certainly seems to phenomenologically a very reasonable conclusion. And this I didn't, and somehow the SYK model also tells you more about charged black holes, but I didn't talk about that. Let me also put up some of my recent collaborators. Maine Christos, a former student, now she's at Caltech. Pietro Bonetti, postdoc now in Stuttgart. Alex Nikolenko, current student, and of course you all know Avishkar. And then I've collaborated with this group of lattice gauge theorists, including Sanjit Sharma, to study more about the finite temperature properties of the FL star state, which I didn't really talk about. Thank you.
I have sort of a naive question. So you mentioned the checkerboard pattern.
Yes. Yeah.
Like I can. So you mentioned the checkerboard pattern in the same.
Yeah.
You're changing the doping level and.
Wait a
At a
minute.
particular doping, you don't see the checkerboard pattern.
You see it at high doping and not low doping.
Correct, correct. So,
Low doping, not high doping. Sorry.
so, and the conclusion you made was